Welcome to lesson number 9, problem solving with linear equations. In algebra, we often solve problems and we often have to solve equations in order to solve those problems. And that's the core of today's lesson. However, I'd like to begin with a few historical notes. If today we would start arguing or discussing about the centrality and importance of equations and problems in the algebra class or in the math class in general, I think everyone would agree that it's very important for students to solve problems and to solve equations. But historically, it's only been about 200 years that problem solving has been central to the mathematics curriculum. It was in Paris at the École Polytechnique where for the first time an educational institution imposed problem solving as a daily activity for the mathematical students. It was such an anomaly and a surprise that mathematicians and teachers from all over Europe came to visit these students to see and watch them solve these very difficult, non-routine problems. Problem solving, however, among mathematicians, among people who advanced the study of mathematics, has always existed. It goes back 4,000 years at least. We have Egyptian papyri, we have Babylonian tablets, we have Greek diagrams, we have Indian Vedas, we have Arabic records, we have Chinese manuscripts. All of these show that for centuries, for millennia, among all cultures, mathematicians have been puzzled by interesting problems. And problems, non-routine problems, new problems, difficult problems, challenging problems, have been the impetus, the catalyst to advance mathematics and in particular algebra. But what I thought you should know is that for about 3,400 years, up until the year 1700 approximately, problems were always very specific problems, problems that pertain to the problems of the day, economics, business, whatever. And it only came until the second half of the 16th century, in the Renaissance period, the Renaissance mathematicians, that they started to abstract and find general solutions, general equations for all linear equations, or all quadratic equations, or all cubic equations. But for the longest time, problems were very particular, specific, and with very specific numbers and situations. Some of the people who are important to know about, who marked milestones along the way in the evolution of problem solving and solving of equations, the one was Diophantus in the 3rd century. He was the first to introduce the use of an unknown. Today we use x or y or z for the unknown that we're looking for in an equation. He used the letter s at the end of arithmos, which in Greek means the number. So that was the first time up until then it was just the language, no symbols, no equations like we know today. Another person who advanced algebra and the science of equations was Al-Khwarizmi in the 9th century. He talked a little bit about solving quadratic equations, but still not much generalization. And then we had the medieval mathematicians such as Leonardo de Pisa, Leonardo Pisano of the 13th century, with his Liber Abaci, the book with all the compendium of problems up until that day. And then again, as I said, latter part of the 16th century, we abstracted ourselves from the particular and went into the universal, abstracted ourselves from the specific and went into the general. So in this lesson today, we have a couple of objectives. We're going to solve problems that will require solving linear equations. We will tackle 2 types of problems. 1, concrete, real-world problems, and 2, an abstract problem. We will use 2 methods for approaching and solving these problems. 1, the functional exploration. We'll look at the graphs of functions. And 2, symbolic manipulation. We will solve equations by hand using the symbols within the equation. So here is problem number 1 for today. In the visual that you see, we have a sequence of figures. The frame, which is in yellow, consists of the bordering tiles in each figure. So in figure number 1, we have 8 yellow tiles that form the frame. In number 2, we have 12. In number 3, we have 16. And the sequence of figures continues to infinity. The question of problem number 1 is the following. a figure in this sequence, somewhere along the way, has a frame of 112 tiles. What is the figure number? Well, let us go to our mathematics laboratory and investigate the pattern of these frame tiles. In figure number 1, we have 8 tiles. Indeed, we have the 4 corners, and we have 4 left over. That's 8. In the second figure, we have our 4 corners, and we have 2, 4, 6, 8. So 8 and 4 corners is 12. And here we have again 4 corners, and we have 3, 6, 9, 12, and 4 corners is 16. Now why do you suppose I separated those corners? So that we can find some type of pattern. Over here we have 4 corners, and we have 4 groups of 1. 1, 1, 1, 1. So we can write this as 4 times 1 plus the 4 corners. Over here, we have, if we leave the 4 corners aside for a moment, we have 2, 4, 6, 8. 4 groups of 2 plus the 4 corners. So I'll write that as 4 times 2 plus the 4 corners. Over here, we have the same. We have 3, 3, 3, and 3. 4 groups of 3, because we have 4 sides of a square, of course, and we have the 4 corners. So that's 4 groups of 3 plus the 4 corners. Well, suppose we went on to maybe this is 1, 2, 3. Suppose we went on to the 10th figure. It would be 4 groups of 10 plus the 4 corners. And in general, if we had the nth figure, we would have 4 groups of n plus the 4 corners. Now, when we'll go to the mathematics technology, the n will look like an x, because our calculator, as we know by now, uses x for their variables. So, we now know the expression for the number of tiles in figure n, that's 4n plus 4. The question says we have 112 tiles in the frame. What figure number is it? Let us find out. Here is the linear equation of the form ax plus b. A is 4, b is 4. X is the input variable. It was the n on our table board, was the figure number. Here, as you know, we use the x variable because that's what the calculator provides us with. Over here we have the y, or output variable. This is the number of tiles in the frame. So if we graph, we have indeed a linear equation. And if we now want to trace, this says that at the 15th figure, we have 64 tiles in the frame. Well, we're looking for 112. So we go all the way up to about 112, and there we are. What do we see? That at 111, we are at the 26th figure, and at 112, we're at the 27th. Now, of course, these are nonsensical because they're not whole numbers. This is the continuous graph, not the discrete one, and in our situation, we have just discrete numbers. So this tells us that probably 27 is our best bet. Let's go to the table. Start with 24, that is fine. Let's have increments of 1. So we're going to start with the 24th figure, and we will see the number of tiles in the frame. Let's go to table. The 24th figure has 100 in the frame. The 25th has 104, the 26th 108, the 27th 112. So this is our winner. All right? What's nice about the table is that you can control the increments, and here we made increments of 1, and therefore we can get just the whole numbers. So indeed, at the 27th figure, x equals 27, we have 112 for the y, which is the number of tiles in the frame. Let us now go to the table board and look at the equation by doing this manually. Method number 2, solving equations by hand. Set y equal to 112, so we do that. And we solve for x. What will x be? 4x plus 4 equals 112. We want to subtract 4 from both sides to isolate the x. So we get 112 minus 4 is 108 equals 4x plus and minus 4 gives us 0. If we now want 1x, here we have 4x, we divide by 4 because 4 divided by 4 gives me 1. 4x by 4 is x. 108 by 4, 4 goes into 10 2 times. I'm left with 2, 28. 4 goes into 28 7 times. This confirms by hand what we saw in the calculator, that x equals 27. The 27th figure will have a frame of 112. Now we also could have solved this in the order that you're probably used to. In other words, 4x plus 4 equals 112. The only difference is that the number is on the right instead of on the left. We do the same thing. Minus 4 on both sides. We get 4x plus 0 equals 108. That's 4x equals 108. We divide by 4. We divide by 4, and we get x equals 27. Either order is the same. I want you to become flexible enough so that you can work it this way or that way and not mind if x comes up on the left or on the right. We are now ready for problem number 2. Here we go. You are given the task of emptying a 15,000-gallon pool. To accomplish this task, you decide to rent a small pump. Its emptying rate is 240 gallons an hour. Question: since renting the pump is quite expensive, you want to figure out how long it will take to empty the pool to see if you can afford the cost of renting the pump. So the question is, how many hours will it take the pump to bring the initial volume of 15,000 gallons down to 0 at a rate of 240 gallons per hour? Here we go. T is time in hours, V is volume in gallons. At time 0, we have 15,000 gallons in the pool. After 1 hour, the difference will be 240 less. So we have 14,760. After 2 hours, another drop of 240 gallons. We now have 14,520. After 3 hours, again the pump has a steady rate. This is a linear function, remember? 14,280. And we can go on and on like this. This is just to give you a pattern. We would have 14,240 less, so that's 040. Well, it would take forever to keep on going this way up until my second column is 0, meaning my volume would be down to 0. But what we can do is use the knowledge of linear functions that we have acquired over the past several lessons, and we notice two things. That the equation is of the form y equals ax plus b. We know what b is at t equals 0, v equals 15,000. Let me mention that this is our V and that this is our T. This always is the general form. So the input and the output, the T and the V. So when x is 0, y is 15,000. That means that our B is 15,000. And what about the A? Well, the A is the change in y over the change in x. Here my change is always 1. So the ratio is negative 240 divided by 1. The increments here from 2 to 3, from 1 to 2, from 0 to 1 are always equal to 1. So this is the first difference, which is the A. So my A is negative 240. So we now can write the equation y equals negative 240x plus 15,000. And the question is, what should x be so that the y equals 0? Let's explore on the graphing calculator. Here is the equation that gives us the volume of the pool in gallons output variable, in terms of the number of hours that the pump needs to empty it, input variable x. Let me show you the window I've selected for you. The number of hours I'm going to guesstimate and say that it's about 72 hours. Hopefully it won't be longer because I can't afford that many days. Over here we have the y. The maximum volume is obviously 15,000 gallons. We could have chosen 0 as a minimum because that's what we want. We want the pool to be empty down to 0. But I went below so that we can see the horizontal axis. Let us now graph the function. Here's the linear function. Up here we have the 15,000, and we decrease, decrease, decrease down to 0. If we want to trace, this tells us that after 36 hours, we'll still have 6,360 gallons in the pool. So I think that it's obvious that as we go down the line, the volume is decreasing, as you can see, by thousands, and we're interested in this value right here. Now let's look carefully. Right before, at 62.04 hours, we have a positive volume. At 62.8 hours, we have a negative volume. So that means that between these two values, 62.04 and 62.8, we're going to empty the pool. That's not exact, but it's close enough. It gives us an idea that it's about 62.5 hours. Let's now look more precisely at the exact value, and I'm going to teach you a new word here. The value of x that will make y 0 is called the zero of the function. Another word for it is the root. So let's calculate that root specifically, precisely. We go to calculate. That's the menu, calculate. We want to calculate the root, so that's number 2. And now it says, what is the lower bound? Meaning, what is the left bound? Well, we have a positive here, so we're on the left of that root. So we select it. And now what is the upper bound? What is the right value of x? Well, you see that's the left bound and the right bound, or the upper and the lower. So we select that one. So that tells us that somewhere in between those two arrows, we're going to have our 0. Well, our guess was about 62.5. Let's see what it is. Oh, and it's exactly 62.5. All right, so right there, where the cursor is blinking, we have the root of this function, meaning the x value that will make the y, the output variable, 0. In this case, it's the volume. So it will take us 62.5 hours to bring the pool down to a volume of 0, and we say that in English. Another way of saying it is to empty the pool. Here we go now to the table board, and let's do this manually and see if we also find 62.5. The equation y equals negative 240x plus 1500. We want to solve this equation for x. That's what we mean by the question mark. When y equals 0, we're setting y equals 0. That's what we want. So we replace y by 0, and now we get an equation with one variable, x. And when we solve the equation, the variable is called the unknown. We're looking for it. It's unknown up until we find it. We can bring this quantity to the left side, which just means adding 240x to both sides. 240x. I now add 0 plus 240x equals 240x equals. This gives me a 0, minus and plus the same quantity. This gives me 15,000. I now want 1x, not 240x, so I divide by 240. I divide by 240. I must always do the same thing to both sides. 240 divided by itself is 1. 1x is just x equals, if you take your calculator, or if you do this by hand, 1500 divided by 24 is exactly 62.5. That is hours and is the answer to our problem. It will take 62.5 hours for that pump to empty the pool. So what have we done? We had a problem. we formulated an equation that gave us the volume of the pool as a function of the number of hours that the pump needs to empty it. We set the equation equal to 0 because that was the value we wanted. Emptying the pool is a 0 volume. We found x equals 62.5. Well, that's about 3 days. You would have to take the pump, if it's a 24-hour fee, so many dollars every 24 hours, you'd have to take it for 3 days. Up to you to decide if you can afford renting that pump for 3 days. Decision-making time. Now we're ready for problem number 3. Here is an arbitrary equation invented by myself, and it doesn't need to reflect any real-life problem. So we can consider this an abstract invented problem. You can invent some on your own also. So we have one unknown. I've put in some fractions here to seem a little more complex or challenging. Let's isolate the x's on one side. So let's add 4x here, so we will get a 0, and let's subtract 3/2 of x over here. But if we do that on the right, we must do it on the left. So let's subtract 3/2 of x, plus, and then add 4x. Here's my equal sign, don't ever forget that, that's like the balance. So on this side we have all these x's. Minus 3/2 plus 1/2 is negative 2/2, but negative 2/2 is a negative 1, so negative 1x plus 4x gives me 3x. Okay. We now have plus 7 that's still left over, and over here this gives me 0, this gives me 0, and we're left with a 10. Now, at this point, you probably would say, well, let's subtract 7 from both sides and write 3x equals 3. But I'm going to pause for a moment and do the opposite. I'd like to subtract 10 from both sides to make a point for a moment. So bear with me. We have 3x. Here we have plus, no, that's minus, because a negative 10 and a plus 7 is a negative 3. And on this side we have a 10 and a minus 10, or a plus 10 and a minus 10 gives me 0. What I wanted to show you here is that we have once again the same situation as in problem 2. We have a function of the form ax plus b equal 0, where the a is 3, the b is negative 3, and the y is 0. This is the form y equals ax plus b, and the question is, what x value will give me a y of 0? So once again, we're looking for the 0 of the function, or we're looking for the root of the function, to use our new terms. So let's go quickly to the calculator to just check and make sure that the solution is going to be that point of intersection with the horizontal axis, and then we'll come back to finish and solve this manually. Our equation was 3x minus 3 equals 0, so we're looking for the y value that's 0. Let me show you the window I've selected for this linear function. These are small values because our coefficients were very small. We're not in the thousands of gallons anymore, so we have a smaller window. Let's graph that function, the 3x minus 3, and what I wanted to show you is that our solution will once again be the root or the intersection with the horizontal axis. Let's trace that, and it looks like it's near 1. Let's go and calculate the root again. That's a new feature that we just learned, so 2 for root. The left of the root would be about there because the root is on the right here. So let's pick that as our lower bound, and it indicates it up there. Let's go now to the right of that special point and select that as our upper bound. And now the calculator will give us the value of that one and only point where the line intersects the horizontal axis. And I'm sure you've already guessed what it is. The root is 1. When x equals 1, y equals 0. Let's confirm this finding by looking at the equation one last time. 3x minus 3 equals 0. If we erase this and just go on solving, I think we can see that we can add 3 to both sides. We have 3x equals 3. It's a very trivial equation. I divide both sides by 3, and I get x equals 1. And that's exactly what I found on the graphing calculator. So we are now ready to recapitulate what we have found and what we have done in all three problems. In problem number 1, y equals 4x plus 4 was our equation. Y was the number of frame tiles, x was the figure number. We set y equals to 112 and we looked for x. We solved for x and we found x equals 27. N was the variable we used on our table board, x was the variable that the calculator used. It was an integer because it was the figure number. In problem number 2, we had another linear equation of the form ax plus b again. Y was the number of gallons, x was the number of hours. We set y equal to 0 this time because we wanted to empty the pool, and once again we looked for x. We solved for x, which is the way we say looking for x. We solved for x and we found that x was equal to 62.5 hours. This value was the root or the 0 of the equation because it was the specific value that gave us 0 for y. In problem number 3, the equation came down to y equals 3x minus 3. We showed that if y equals 0 and we look for x, we found that x equals 1. Once again, this was the root or the 0, and it was represented by that x value of the point that we call the x-intercept. Problems number 2 and 3 ended up being ax plus b equals 0. We looked for the roots. Let me go back to problem number 1 for 1 second and show you that that one also could have been brought down to that form of equals 0. Problem number 1 revisited. This was the equation. We set y equals to 112 and we found x equals 27. I challenge you to try the equivalent equation, which would be subtracting 112 from both sides rather, and we get 0 equals 4x minus 108. This equation looks different from that equation, but they are equivalent. And the point I want to make is that this equation is written ax plus b equals 0. All linear equations can be brought to this form. The solution of this one is the same as the solution of that one. We are now ready to recapitulate and to generalize for all linear equations, not just for the 3 that we saw today. F of x, or y, equals ax plus b is a linear equation in 2 variables x and y, where a and b are the constants. In this form, it is a function. It is a relationship between x and y. It does not ask to be solved. In fact, it has an infinite number of solutions, x1, y1, x2, y2, x3, y3, which are none other than all of the xy pairs, which are the points that live on the line. Given a specific value of y, x can be determined uniquely. We say that we solve the equation for x, and x is then called the unknown. It is unknown during the process until it is found. All linear equations in one unknown, usually x, but it can be any variable, can be written in the general form 0 equals ax plus b, or ax plus b equals 0. That they're commutative, so it doesn't matter which order. They are equivalent. They have a unique solution, which is called the root or the 0 of the linear function y equals ax plus b. Once again, x is called the root or the 0 of the linear function, or any function, as a matter of fact, if it is that one value that will make the function 0. And we saw that we find it at the intersection with the x-axis. So I hope that this lesson has helped you connect linear functions with linear equations. A linear function is a line. On that line live many points. Those points have x, y values, input, output, independent, dependent variable, x, y. Many points live on the line. As soon as you give me a specific y value, be it 0 or be it something else, we locate the x and we find it uniquely. That's what it means to solve an equation. Find the x value that satisfies the condition that you are given or that you pose.